Welcome to this Explainer. Today, we're unpacking 4 major scientific breakthroughs and the highly efficient systemic machinery that erased the women who actually made them. Let's dive right in.
Let's open with a pretty stark contrast. On one side, it's December 1962, and James Watson, Francis Crick, and Maurice Wilkins are accepting a Nobel Prize for discovering the double helix structure of DNA. On the other side, Rosalind Franklin's headstone in London. Notice the dates, 1920 to 1958. 4 years before that Nobel ceremony even happened, the woman who took the defining photograph of DNA had passed away. So if a Nobel Prize is for the work, why was the person who actually did the heavy lifting excluded from the narrative?
That brings us to Rosalind Franklin. With a doctorate from Cambridge and specialized training in Paris, she was the world's leading expert in X-ray diffraction. Honestly, she was the closest person on the planet to solving the structure of DNA. As you'll see, it was her exact image and precise experimental setup that finally made the double helix visible to the world. 15. That's the number of hours Franklin and her student Raymond Gosling exposed a DNA fiber to an X-ray beam back in May 1952. 15 grueling hours. What they got was photo 51. Because she maintained such intense, meticulous control over her lab environment, that film captured a sharp, clear X shape right in the middle. It was the direct visual signature of a double helix. Her own notebooks already concluded that the structure was helical, with phosphates on the outside. She had literally captured the architecture of life.
Then, without her knowledge and definitely without her permission, her colleague Maurice Wilkins showed photo 51 to James Watson. Listen to Watson's own words from his memoir. "My mouth fell open and my pulse began to race." He knew exactly what he was looking at. 3 months later, Watson and Crick published their model. In their acknowledgments, they mildly mentioned being stimulated by a general knowledge of her unpublished work. Talk about an understatement. They completely glossed over the fact that her 15-hour photograph was the concrete foundation of their entire model.
Now, this pattern of exclusion absolutely wasn't isolated to biology. Let's talk about Lise Meitner. For 30 years, she collaborated with Otto Hahn in Berlin, building one of the top partnerships in nuclear science. But in 1938, as a Jewish woman under the Nazi regime, she was forced to flee Germany. She crossed the Dutch border with virtually nothing but a diamond ring, a ring Hahn gave her just in case she needed to bribe a border guard.
While walking in the Swedish snow with her nephew, Meitner worked out a massive theoretical physics problem. She calculated how a heavy uranium nucleus absorbs a neutron, elongates, and splits. Using Einstein's mass-energy equivalence, she figured out that this process converted a tiny fraction of mass into an immense 200 million electron volts of energy. She literally did the math in her head during a winter walk. She even coined the term for it, nuclear fission. And yet, Otto Hahn published the experimental results with only his name on the paper, completely leaving out her theoretical breakthrough.
48 times. Think about that. Lise Meitner was nominated for a Nobel Prize 48 times over her lifetime across physics and chemistry, and she never won it once. The 1944 Nobel Prize in Chemistry went to Otto Hahn alone. Albert Einstein called her the German Marie Curie, and eventually element 109 was named Meitnerium in her honor. But let's be real, a posthumous element name doesn't change the fact that she was totally erased from the defining paper of her own career.
Jumping to a completely different decade and field, we meet Jocelyn Bell Burnell. In 1965, as a 22-year-old PhD student at Cambridge, her project wasn't just to use a radio telescope. No, she actually had to build it. She spent 2 years out in a field hammering stakes and soldering wires by hand to construct a massive 4.5-acre piece of equipment. When they finally turned that telescope on, it churned out 400 feet of paper chart every single day. Bell Burnell analyzed all of it, entirely by hand, physically running her finger along the printouts to spot anomalies. And she found one, a 1/4 inch of scruff that just didn't fit. Her supervisor, Anthony Hewish, quickly brushed it off as television interference or a passing satellite. But she wasn't buying it.
She kept pushing and eventually captured a signal pulsing perfectly every 1.33 seconds. It was so perfectly regular they even joked it might be aliens. What it actually was the very first observational evidence of a pulsar, rapidly spinning neutron stars blasting beams of radiation across space. It was a massive, universe-altering discovery. So who got the 1974 Nobel Prize for discovering pulsars? Her supervisor, Anthony Hewish. Bell Burnell was left out completely.
Decades later, she was awarded the Special Breakthrough Prize in Fundamental Physics, which came with a staggering $3 million. She didn't keep a dime of it.
She donated the whole thing to fund underrepresented students in physics, saying she didn't feel right keeping it for a team effort. When journalists asked if she was bitter about the Nobel, she just calmly pointed out that if a young woman had won it back then, everyone would have just dismissed her as a lucky student. That quiet observation really hits the nail on the head about how credit works in science.
Section 4. Chromosomes and Nettie Stevens, the discovery of biological sex. Back in 1905, people thought biological sex in animals was determined by environmental temperature or some innate vital force. Nettie Stevens studied the mealworm beetle, and through some intensely meticulous microscopy, she discovered that biological sex is actually fixed at fertilization by chromosomes. She specifically identified what we now call the X and Y chromosomes. In 1905, Stevens published her clear, complete findings. Her paper came out first and was way more comprehensive than her male peer, Edmund Beecher Wilson, who published similar findings later that same year. Yet when Stevens tragically died at age 50 in 1912, her own mentor, Thomas Hunt Morgan, wrote her obituary and explicitly gave Wilson the primary credit for the discovery. Morgan himself later won a Nobel Prize heavily based on the chromosomal framework she helped establish, completely leaving her name out of it. Because of this, she practically vanished from textbooks for 70 years.
Section 5. The Matilda Effect, Systemic Analysis and Contemporary Evidence. We've just looked at Rosalind Franklin, Lise Meitner, Jocelyn Bell Burnell, and Nettie Stevens. That's 4 scientists, 4 entirely different scientific fields across 4 countries. What we're staring at here is one undeniable systemic pattern.
It's called the Matilda Effect. Basically, it's the systematic under-recognition and appropriation of women's scientific contributions. Sociologist Margaret Rossiter coined the term in 1993, naming it after Matilda Jocelyn Gage, a suffragist who first wrote about this exact type of appropriation way back in 1870. When you look at the history, it proves this wasn't just a string of bad luck or simple misunderstandings. It was a highly functioning machine.
And this machine operates using very clinical mechanisms. First up is the attribution shift, where credit for collaborative work just automatically defaults to the male peers. Then there's the obituary gap, where a woman's achievements conveniently vanish from the official record the moment she dies, exactly like we saw with Stevens. Finally, the student default, meaning any discoveries made by female students are effortlessly handed over to their male supervisors, just like what happened to Bell Burnell.
Now you might be thinking this is all safely in the past. It's not. Data from 2022 shows that, even when you control for all other factors, papers with female first authors still get significantly fewer citations than equivalent papers with male first authors. This system of attribution inequality is still humming along in the scientific community right now. It's not a historical artifact. We are dealing with it in the present tense.
But despite all this erasure, there's a big reason for optimism. The paper trails still exist. Rosalind Franklin's 15-hour exposure photos and lab notebooks, they're still around. Lise Meitner's precise calculations survive in her letters. Jocelyn Bell Burnell's original observation printouts from 1967 are preserved, and Nettie Stevens' reports are sitting safely in the Carnegie Institution archives. The evidence of their genius was always there, just waiting for people to finally read it right. Knowing exactly how efficiently this erasure machine operates, we have to ask ourselves a pretty huge question. What other world-changing discoveries are still sitting quietly in the archives, just waiting for their rightful authors to finally get the credit they deserve? Keep that in mind the next time you crack open a standard textbook. Thanks for hanging out for this explainer, and remember to always question the history you're handed.